This is Francis Bitter's magnet laboratory at MIT. We're fortunate enough to be able to use some of the apparatus here for our demonstrations of magnetic forces. You're all familiar with electromagnets. They consist basically of a coil of wire through which a current passes, producing a magnetic field, like the electromagnet in this doorbell buzzer here. Now, the current requirements of this electromagnet are quite small and can easily be supplied through light wire, like this lamp cord here. The electromagnets in the magnet laboratory are basically the same. They consist of coils through which currents pass, producing magnetic fields. For most of the problems studied in this laboratory, strong magnetic fields are needed, so that the currents through these coils have to be very, very large, and the coils have to be cooled by hundreds of gallons of water a minute. The very large currents, 10,000 amperes or so, reach the magnets through these bus bars overhead, like the one Dr. Bitter will show you over there.
Here we have the bus bars that carry the current around the laboratory and can be fed through switches to any one of several magnets, like the one here. If you close this knife switch like this, to carry the current on to the heavy leads here coming to the magnet. Here, the terminal which brings in the current is connected to a smaller coil which goes from this plate to this one, out of this electrode, out of this bus bar, through this switch, and out, so to complete the circuit. This coil would be melted in a small fraction of a second, I think, if it weren't very effectively cooled by water coming up from below and through the coil and out through these pipes that you see here. This magnet is used to measure the magnetic properties of very feebly magnetic substances. By connecting a specimen from the middle of the coil where the magnetic field is created through a fine wire or string, through this tube here, to this very sensitive microbalance that Mr. Lin is adjusting here, we can measure the very small force which even this strong magnetic field produces on relatively non-magnetic materials like copper, aluminum, oil, water, and so on. Here we have a second electromagnet, and back there a third one. And over here we have a couple of researchers connecting up the very last word in magnets as movable and efficient. As John has said, this movie is about magnetic forces, like the forces of attraction between these two permanent magnets and the forces of repulsion. These are the forces which drive all electric motors. We want to demonstrate in this film that magnetic forces are due to electric currents. This you can show perfectly well in your own classrooms and laboratories with very modest equipment. Since we have here, however, these big currents, we want to use them to put on a new kind of demonstration that we've never seen ourselves. We're going to use the magnet laboratory just for having fun this time. In order to get the currents into these big bus bars, we have to turn on the big motor generator out there. We're going to take you out to have a look at it, and you might notice that very considerable forces are required to move the very heavy machines we have out there. Those are magnetic forces. Okay, Beans, you all set to fire it up?
Yes, sir.
This is the machinery that provides the current for the electromagnet. It consists of a motor operated by current from the power lines and a generator, which provides the current for the magnet. I think the size of this apparatus gives you some feeling for the forces that are required to turn it over, and some feeling for the current that we will be using in these
thing we're going to want to show is something about the forces between currents. That's something we know about in the magnet lab, isn't it, Henry?
At least we're finding out rapidly. We sometimes try to generate very high magnetic fields for very short periods of time by putting very strong current pulses through small coils. We just cut open one here, which holds the world record right now.
Yes, the currents go around this way, don't they?
That's right.
No.
Of course, we've made many before this one which didn't hold up, and here's one that blew up. The conductors were forced outward, making it look like a barrel.
Well, here comes John. Now we want to show you something about the forces which currents and conductors exert on each other. These, in general, can be very complicated. In fact, if we wanted to describe the force on some little piece of conductor here due to the currents flowing in the whole thing, we'd have to take all the currents into account. Before we're through, we're going to have to consider the whole idea of a magnetic field to describe these forces. However, to begin with, let's take the simplest case possible of two parallel wires like this and examine the forces which they exert on each other.
The biggest problem I have with that is trying to remember which way the forces go. So we're going to demonstrate it in a way that I think makes remembering it easy. Here we have a bundle of parallel wires, all connected to a bus bar up at the top. Currents flow down through these wires, all in the same direction, and out through this copper strap to another bus bar over there. Okay, let's see what happens when we pass current through it.
All right, Beans, let's have a little juice here, and let's start gently. Let's have about 1,000 amps to begin with. Takes a minute to build this all up.
You want it on the telephone.
Oh, tell them to call me back later. I'm busy. How's it coming, Beans? You got it? All right, let's go on up to 2,000. There we begin to go.
2,000.
On up to 3. Let's show it really.
3.
Oh, there we go.
4. 5.
I guess that's enough. Let's cut it off. Well, I guess there isn't any argument about which way those forces are working. When currents are moving in the same direction, they attract each other, and you can see that by the squeezing up of this bundle of wire.
You've seen what happens when we have currents flowing in the same direction. This time we're going to see what happens when the currents flow in opposite directions. The current comes in from the bus bar through this flexible copper strap, down through this solid copper rod, and back up the other side, and out this flexible copper strap. Now these are solid copper rods. They don't move easily, and the current on one side goes that way, and on the other side goes this way. Now let's see what happens. You may fire when ready, Maestro.
Okay, Beans, this time I want you to set the equipment so that when you close the circuit breaker, you get the full output of the machine through these all at one crack, and stand by to open it up in case we get any trouble with it. Okay, let's take it away. Yeah, there it is, going out.
There, you see how far it's spreading apart? Now those are solid copper rods.
There she goes. Whoa, cut it off.
Okay, fire's off.
Did you see the flash out there? That was the circuit breaker that opened the circuit when we were getting too much current through the machine.
Okay, go ahead.
500, 1,000, 2,000, 4, 5.
Let's get going on the next experiment. You make the connections while I say a word
Okay, I'll
about
go
it.
get started.
This is a magnetic compass needle that's used to explore the field of the Earth. And we want now to use a compass needle like this, or a whole lot of them, to explore the field around a current.
Well, here we have a loop through which current comes in to these copper straps here, flows through this loop made of copper bars, out around this way, and out through these copper straps to the bus bars. Now we're going to study the magnetic field due to current flowing in this copper rod. We're going to explore it with the help of all these compass needles here. Now right now they're all pointing approximately north and south due to the Earth's magnetic field. I say approximately because this is after all a magnet laboratory, and there are plenty of stray magnetic fields around here that are as big as, if not bigger than, the Earth's field. Okay, Beans, let's have about 1,500 amperes through the wire. And now you can begin to see some activity. They wiggle around and start to line up in the form of circles going right around the rod through which the current is flowing. All right, Beans, let's reverse the current now. We have to turn it off first and then reverse it. Now, you think you can see what's going to happen? We're going to turn around and point the other way. Now you can see they all point in circles around this way. Okay, Beams, that does it on the current. Cut it off. The lines of magnetic field are circles around the current, and they reverse direction when the current reverses.
Now we want to show you an experiment involving this good old lecture demonstration magnet, which isn't part of the magnet laboratory at all, really. We need to have a magnetic field, and we can get it here between the poles of this magnet very conveniently. I'll just turn it on. Oh, I better watch my watch. I get it magnetized so much I get sick of having it demagnetized. I have to get along with just setting it every time I see an electric clock. Well, now we have a magnetic field here, and there's a very simple little way of showing this with a few little nails. I think you can see that we have here a magnetic field going from this pole to this one. Now we want to talk about the forces on a current-carrying conductor in a magnetic field. In an earlier experiment, we showed you about the forces between currents. Now we want to leave out the notion of the other currents and really discuss just the force on the conductor in terms of the magnetic field which is present where the conductor is located. I'll put this in here, and we can pass a current through it, through the little mercury cups into which it's dipping by means of these wires, so that we'll have a current at right angles to this magnetic field. All right, let's turn this on. I think you saw that we had here a vertical force upward on this current-carrying conductor when it was at right angles to the field. And whenever you have a field like this, horizontal, with a conductor carrying current at right angles, we'll have a force at right angles to both, an upward force in this case. Magnetic fields are produced by electric currents. In a circular loop of wire of this kind, a circulating current will produce a magnetic field that goes through the wire. If we have a whole series of turns of this kind to form a cylindrical coil, the magnetic field will be driven in at one end and out of the other. This is, in effect, a cylindrical magnet, and we want to discuss whether we can describe the magnetic field produced by a magnetized iron bar of this kind in terms of currents. Clearly, we have strong magnetic effects of some kind, and the question is whether this must be described in terms of a new concept of poles in a piece of magnetized iron, or whether currents will do. If currents can be considered in this connection, they must, of course, be atomic currents, not macroscopic currents. There are no wires connected to this, and this is a problem for atomic theory. an atom may be thought of as having a positive nucleus and a cloud of negatively charged electrons around it. And if this cloud of electrons is rotating, it will produce a circulating current of this kind, and the field due to this current may be thought of as very much like the field due to a circulating current through the wire. It will drive flux or magnetic field through the atom. And if we have a lot of these side by side, they will all drive field through the individual atoms. And in a magnetized piece of iron slab of this kind, we may think of magnetized atoms as being lined up so that the currents are circulating in the same direction, and these circulating currents drive flux through the whole business and produce a field very much like that which is produced by the single circulating current in this wire. Now, if we take a lot of slabs of iron of this kind that are magnetized and put them together to form a cylindrical rod, we see that all the circulating currents of the individual atoms may be thought of as driving magnetic field through the whole magnetized bar and out of the other end, and producing an effect very much like that of a solenoid of this kind. Now, John has been setting up our last experiment, and we want to examine a little further the nature of this comparison. Now we want to show you in this last experiment a little bit more about the nature of this interaction of a current in a conductor with a magnetized magnet. That's what John's been setting up here.
Well, here we have a pair of electromagnets. They're coils of wire through which we can pass a current. Now, we've arranged these in such a way that the magnetic field due to this one is in the opposite direction as the magnetic field due to this one. And we shall detect the magnetic field at this point in the center by means of a compass needle.
So this turns out to be kind of a magnetic balance,
That's the idea. When we get them exactly balanced, there won't be any magnetic field right in the middle, so that the compass needle will show.
Well,
why don't you put on a little current through yours? We'll see what happens. So there we have current flowing through this one, a magnetic field attracting the compass needle. All right, now I'll turn mine on and see what we get. So far, just exactly nothing. So let's raise the current a little bit, give her a spin to get it off dead center.
Well, that looks as if yours, well,
now
just about
balanced. Mine's going to be stronger than yours now.
A little bit stronger.
Yeah, okay, so I'll back mine off a little bit and make it a fair game.
Now it's weaker.
Now, here we have a bar of iron. I'm going to put the bar of iron inside this magnet so that the iron will, as you know, become magnetized, and its magnetic field will add to that of the current. Oh, it looks like I'm winning this time. See what you can do.
I don't know. I don't know.
Here.
Haven't got very much poop here, but I have an idea. What do you say if we try to connect up the old iron sides out here and see if we can put enough current through that copper winding to counterbalance what looks like currents flowing around that iron rod?
Okay.
There's one bus bar connected onto here through a couple of good straps. And there we are. Now, are we all clear?
Fire away.
Okay, Beans. I guess we're ready for a little juice.
Okay, here it comes. 1,000.
Fly ahead. Yeah, keep going, yeah. Oh, I guess we haven't made it yet. Oh, it's beginning to melt. Oh, we haven't made it yet. Okay, Beans, I think that's enough. Well, I guess we didn't have quite enough current there to really equal the magnetization of the iron. I suppose it's clear now that the magnetic effects of magnetized iron are stronger than anything we could produce by driving currents through those coils. How is this possible? It's because within each iron atom there are such strong circulating currents. Because in the iron rod we were able to line up these currents, and finally, because in the rod there are so very many atoms.